So let's begin the first chapter in the real physics. We have covered estimation, measurements, and experimentation. And let's now go into the some aspects of physics, starting with motion. And the study of motion is called kinematics. And this chapter is about one dimensional motion. And one dimensional motion means the body moves in a line, on a line. It could move left, it could move right, it could go with a constant speed, or it may go with a varying speed. But it is constrained to move along that particular line. Now, that line we may call x axis or y axis or z axis or whatever. So that is a study. So we are going to learn about what is motion. How do you describe motion? How do we measure it? And what are the relationship between various motion parameters? So first of all, let us understand the concept of position vector. We have our axis, the origin here, the x and y and z axis, and we have a point P located somewhere. How do we denote the position of the point P with respect to this particular coordinate axis system? That is the distance OP. Now, it is not just the distance OP, it is also the direction OP. So, the direction is this vector called position vector of the point P with respect to O, which means you draw a line from O towards P. It has got a certain length, it has got a certain direction. That is a position vector of P with respect to Q, with respect to O rather. Suppose I have another point Q, then that position vector will be this one. Draw a line from O towards Q, and that is a position vector. But we could also talk about the position vector of Q with respect to P. That means draw a line from P towards Q. That would be the position vector of Q with respect to P. Now, when a body is moving, what is happening basically is this, that the position vector that we have would change with time. Say this particular body, which is currently at this particular point P, if it is moving, then it may move this way, it may move that way, whatever. Then the length of this vector as well as the direction of the vector may change. So then that is called motion. But very important to realize that what is the position vector depends on the reference point, which is the origin. Right? So any position vector is with respect to a particular reference point, which we usually call the observer. Observer means he is located at the origin. Now, when is motion said to occur? Say, suppose we are an observer. Now, the observer is the origin. And a car is moving along this black arrow. So, right now, the position vector of the car with respect to the man is this, right? And as the car moves forward, the position vector changes. You can see the length of the vector has changed and the direction has also changed. Again, the car moves forward, the position vector has changed. Again, the car moves forward, the position vector has changed. So motion is said to occur when the position vector of the body with respect to some observer changes with time. And if it doesn't change with time, then there is no motion. But remember, this is a vector. Its magnitude may change, or its direction may change, or both may change. In any of the three cases, it has changed, right? And if it has changed, then there's a motion. Now, let us see some examples of magnitude or direction or both can change. Let us see the first diagram. The observer is here, and the body is this red one, and the body is going like this. So right now, the position vector of this point with respect to the observer is this RI, let me say, initial position vector. And later on, the body comes in here, then the new position vector is this. Final position vector is this. That vector has changed in the length, not in the direction. So here, only the magnitude has changed. That is a motion. The magnitude has changed, so the position vector has also changed. That is a motion. Second example, a body, the red body, is going around in a circle with the center being at the observer. So right now the position vector is this Ri. After some time it comes in here, then the new position vector is this. Clearly, because this is the radius, the length of the radius doesn't change. That means the magnitude of the vector doesn't change, but the direction has changed. Earlier it was like this, now it has turned. So only direction has changed. Well, that implies that the vector has changed, so there is a motion. Third case, the observer is here and the body red one is moving to the right. So right now the position vector is this. After some time the body comes here, so position vector now is this. Clearly the length has increased, that magnitude of the vector has increased, and the direction has also changed. So both magnitude and direction have changed. In all these three cases, motion is occurring. The position vector has changed. All right. But the point is, any position vector is with respect to a particular observer. So here I have two observers now. Observer 1, which is at rest sitting on the ground, and observer 2 is not at rest. He is moving with a certain speed, and the body, the red one, is also moving with the same speed and the same direction. Now, what will the two observers say about this particular body? Will they say the same thing? Well, the first observer will say that the body is going away from me, the new position vector is going to be larger. So the body is going away from me with the speed v, it is moving. That is what observer 1 will say. What about observer 2? Right now the position vector is this. After some time, when this guy comes in here, well, the observer also has moved because the observer is going with the same speed and same direction. Observer has also moved. The new position vector is this. The new position vector of the body with respect to the observer, right? Now, these two vectors, Ri and Rf, are exactly the same. The length is the same, the direction is also the same. Therefore, observer 2 is going to say something different. The body is not going away from me, it is not moving, it is at rest. The position vector of the body with respect to observer 2 is not changing. So you can see the interesting case where a body is supposed to be moving as per observer 1, but as per observer 2, it is not moving at all. All motion is relative. There is nothing like absolute rest or absolute motion. Everything is relative to the observer. Practically, I can give an example of this exact situation that there is a person standing on the ground and there's a car going with some speed, and observer 2 is sitting in another car on the same road, and those two cars are going with the same velocity on a straight road. Then this person will say that this car is moving. He will also say that this car is also moving. But this person will say that this car is not moving. All motion is relative. So let's start discussing 1D motion. When a body moves along a straight line, it is called one-dimensional motion. It can reverse its direction while being on the same line. That means its direction can change and its speed can also change. It can increase or decrease its speed. For example, this car on a straight road is going away from us, right? But it can reverse also, no? So that is 1D motion. Or a train going on a straight track, that is also 1D motion. Or a stone that is released from a certain height, it falls through, it goes on a straight line. All these are examples of one dimensional motion. Now, in physics, we often say particle. Particle means the size of the body that is moving is rather small, but nothing is small or large by itself. It is in comparison to something. So, in physics, when you say particle, it means that the distance moved by the particle in a certain time is much larger than the size of the body. Then we can approximate it to a particle, means a point mass. A particle is a point mass which has got a mass but no appreciable length or breadth or height. That's a particle. What are the parameters? So we learned about what motion is. How do we study the motion? Now, whenever you want to study something, for example, if I were to say that please give me a report on the climate of Bangalore, what will you study? You will study the temperature, the rainfall, the humidity, and some other parameters. And you will not only measure it on one particular day, you'll measure it on a daily basis for maybe a year or maybe 2 years or 3 years. Only then can you have some data and then you can say, well, the climate is so and so. So, similarly, when we are studying motion, we need to have some parameters based on which we can describe that motion. And those parameters are distance, displacement or position, speed, which may be an average speed or an instantaneous speed, velocity, average or instantaneous, acceleration, average or instantaneous, and of course, time. These are the parameters which we are going to see. Now, it will always be study of displacement as it changes with time, or study of velocity or speed as it changes with time, or study of acceleration as it changes with time. Changes may increase, may decrease, or may not increase or decrease. So, whatever it is, study of those parameters with respect to time. So, let us discuss each one of those parameters. So, in this session, we are going to talk about distance and displacement. And in the next one, we'll talk about speed and velocity. And in the next one, we'll talk about acceleration. Distance. What is distance? Let us first see a particular kind of motion which, as we have just discussed, every motion is relative to a particular observer. So here we have an observer located at this point, and that usually we designate as that as the origin, and it is moving along the x-axis. It's a 1D motion, it's moving along the x-axis, and this point is the origin, that means x equal to 0 meter. When we started our study, the body was located here. So that is at the start. When we say start of the study means we designate time is equal to 0. At that time t equal to 0, the body was at a location 6 meters away from the origin. That was the start. Now, suppose we have got a camera which takes a picture of that particle every 1 second. Just takes a picture of the particle every 1 second. So after 1 second, this t is equal to 1, the body is at 8 meters away from the origin. At t equal to 2 seconds, that is after one more second, it has moved to a point 10 meters away, and so on. What do we observe? In the first 1 second, it has gone from 6 meters away to 8 meters away. That means it has gone 2 meters away. In the second, it has gone from 8 meters away, that was the position, to 10 meters away. Position has changed by 2 meters. Like that, in every second, it is doing only 2 meters, 2 meters, 2 meters. In every second, it is going away by 2 meters. We say it is covering equal distances every second. That is equal distances in equal times. That is called uniform motion. All right. Suppose we have another picture of another body. In the first 1 second, it covers 5 meters. In the second, it covers 20 minus 5, 15 meters. In the third second, it covers 45 minus 20, that is 25 meters. In the fourth second, it covers 80 minus 45, that is 35 meters. Now, what do we see? We see that in successive seconds, it is covering larger distances. It is covering unequal distances in equal times. That is called accelerated motion, right? So when you have equal distance covered in equal times, then that is uniform motion or constant speed. When it is unequal distance in equal times, then the speed is changing from time to time. That is called accelerated motion. Conversely, we can say that if in unequal times it covers equal distances, in unequal times it covers equal distances, again the speed is not constant, it is a case of changing speed or accelerator. So, talk about distance versus displacement. You can see this picture. It's a mountain road. You can see there's a road going and there are cars. The picture from quite some height. And I've denoted a point A and a point B on that road. Suppose I want to go from A to B, sitting in my car. How will I go? Along the road. Along the road, I will go. And my car indicator will tell me how much distance I've covered when going from A towards B. But suppose I was in a plane or something, then I could go directly from A to B like this, straight line. That is the displacement. Distance is the length of the path taken when going from one point A to another point B. You could have multiple paths, right? I have shown you two paths. Whatever is the length of the path, that is a distance. Whereas a displacement is only a straight line joining the initial point to the final point. It's a straight line and it is a vector as well from the initial point to the final point. So the line joining AB in this case is actually the displacement vector. But if I talk about the magnitude of the distance, that is the path length, and the magnitude of the displacement, that is the length of the yellow arrow, clearly the distance is more than the magnitude of the displacement, right? So distance is a path length, it's a scalar quantity, it is measured in meters. Displacement is a vector quantity. Its unit is meters, magnitude is meters, but it is a straight line length from initial point to final point, and displacement doesn't depend on the path taken because it is only a line joining the initial point to the final point. You can take whichever path, but we don't care about the path once we are talking about the displacement. Therefore, the distance is always greater than or equal to, I'll draw two lines like this, meaning magnitude of the displacement. All right. So very interesting things come up because of this definition of distance and displacement. Suppose you have many small straight line displacements of a body. What is the net displacement? The net displacement S and vector means we draw an arrow is the vector sum of the first displacement with the second, with the third, with the fourth. There may be n displacements. There are n small straight line displacements. Total displacement is a vector summation. Whereas the distance is not the vector summation. This is the magnitude of the path that is taken. Then the distance is the magnitude of the first displacement plus the magnitude of the second displacement plus the magnitude of the third displacement and so on up till n, right? So this is a little bit misleading. We'll just call it distance, right? Take an example. I start from A and I come to this point, let us say C, via a straight line displacement S1. Then I go from C to a point D via a straight line displacement S2. Then I go from D to E via a straight line displacement S3. Then I go from E to B via a straight line displacement S4. What is the net displacement? The vector sum of S1, S2, S3, S4. Now there's a rule of vector addition, which you are going to learn in 11th standard, that if you have to add many vectors, then you arrange them tail to head, tail to head, tail to head like this. This is the tail, this is the head. Tail to head of the first vector, tail to head of the second vector, tail to head of the third vector, tail to head of the fourth vector. Suppose four vectors you're adding. When you arrange them tail to head, tail to head, tail to head, and the sum of these four vectors is a line joining the initial point to the final point. That is the sum of those four vectors. So in this case, what is the sum of S1, S2, S3, S4? Tail to head, tail to head, tail to head, tail to head. Join the initial point to the final point. That is our net displacement. It has got a magnitude, that is the length of the line AB, and it has got a direction. That is a displacement. What about the distance? The distance covered is not the length of this arrow. You went by this road, right? The distance is all the way like this. So magnitude of the first displacement plus magnitude of the second displacement and so on, then that is how you get the distance. So two things are very different. Interestingly, if you have a closed loop, suppose you start from here and come back here, you start from the point A and go along this path and come back to A. What is your displacement? Displacement doesn't care about the path. You just join the initial point and the final point. The length of that line will be the magnitude of the displacement. But if you're coming back to the same point, then the line joining initial point and final point is basically a point. It's not even a line. Then the displacement is zero. If you come back to the original point, you may have gone all over the world, but you have come back to the same point. The displacement is zero. Whereas the distance would be the path that you took. Suppose I start from Bangalore, go to London, New York, Sydney, and back to Bangalore to my house, my displacement is zero. But the path length is many thousand kilometers. I went to London, then New York, etc. So distance is always greater than or equal to the magnitude of the displacement. It will be equal to the magnitude of the displacement only in one special case when it is the body is going along a straight line path from one point to the other. Then distance is equal to the displacement in magnitude, right? So to summarize, distance versus displacement. Distance is the length of the path taken by the body. Length of the path. It depends on the path. Magnitude of the displacement is the distance moved in a specified direction. So the total displacement vector would be the distance moved in a specified direction, that is a straight line joining the initial and final points. Distance is a scalar quantity, displacement is a vector quantity. Distance is just a positive number, say 5 meters, 20 meters, 100 kilometers, just a positive number. But displacement being a vector can be positive or negative depending on the direction. We have a sign convention to denote the direction of vectors, and we will talk about later. So displacement can be positive or negative. The distance can be more than or equal to the magnitude of displacement that we have already seen. The displacement doesn't depend on the path taken, and in a closed loop it is zero. Whereas distance is never zero. As long a body is moving, it may be going round, round, round in a circle. As long as it is moving, it is covering some path all the time. The distance is never zero. And also one more thing. As long as the body is moving, the distance covered by the body is only going to increase, it's never going to decrease. So you're sitting in a car and you're going round, 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 your meter is going to say that you have covered so many kilometers, right? So the distance covered is never going to decrease, right? So I hope this basic concept is clear. In the next session, we'll talk of speed and velocity.